Welcome to the recording of section 3E. This is the last section we're going to cover in chapter 3. The section 3E, I think, mainly covers two topics. One is we're going to define the product of vector spaces. Hopefully that's a relatively familiar concept for most of you, or you probably have seen that in another like topology class, or maybe intro to proof class, or maybe like even discrete math class. And then we're going to use that definition and also define a special map, and then use that to get a desired result, which says if you have the subspace like U1, U2 up to UM, which is the direct sum, you add it together as direct sum, the dimension of the direct sum equals the sum of the dimensions of those individual subspaces. That's a very, I think, natural intuitive result. So this, I think, is the first part of what the section 3 is going to cover. We're probably going to make that part as this recording. And then after we finish the product spaces, then we're going to go to talk about the quotient spaces, which I think is probably a relatively newer idea for most students. And then we're probably going to make 1 or 2 recordings to cover the basic concept of the quotient spaces, and then cover some properties for the quotient spaces. So that's the plan for the section 3E. All right. So let me go ahead and share the screen here. Okay, good. All right. So 3E, the products and the quotients are of vector spaces. So let's first define the products. Okay. So let's talk about the products of vector spaces. So the definition is, I think this is 371, or the definition here says, suppose there are like V1, V2 up to Vm. These are vector spaces. These are vector spaces over the same field F. All right, so all these vector spaces need to go over the same field F. And then the product V1 times V2 times up to V sub m. This is defined by, so this right now this is a new set, using the given sets here. So we're going to form this should be the lowercase letters in the pair of parentheses here. All right, so those are the vectors V1 taken from the subspace V1. The second component is a vector V2 taken from the vector space V2, and so on. All right, so where does V1 belonging to the capital V1, V2 belonging to capital V sub 2, and the last one V sub m is belonging to capital V sub m. All right, so this is a collection of the objects, right? So we have done this several times before. Is once you have a collection of the objects, we're going to think about define some operations over those elements in this set. And then here we're going to naturally define the addition. All right, so how to add those two vectors in this cross product space together, and then define the scalar multiplication. So those are the two things we want to define. All right. So the addition on this product right now is a set. All right. This is defined by, so if you have some U1 up to U sub m, and then V sub 1 up to V sub m, then this is just U1 plus V1, U2 plus V2, up to UM plus Vm. All right, so this is exactly the same fashion as how we define like the sum of the two vectors, right, maybe in Rn, right? Obviously, this is not in Rn because U1 itself can taken from any vector space V sub 1 there. Right? It could be a polynomial if you think that's from polynomial vector space. It could be like a vector of lengths of the length 3, right? 3 entries if the V1 is R3, right? So this is and then similarly the V2 can be anything from any vector space. All right, so you can make this product among any kinds of vector spaces, form this product, and then the scalar multiplication are on this same V1 times V2 up to Vm. This is defined by also a very familiar definition here. If you have any V1 up to Vm, and then this lambda will distribute on every single entry in this vector here. All right. So then everything hopefully sounds very familiar, all right? But just to make it clear, all right, so we really do not mind, all right? Of course, in the application, we want something meaningful, right? But in terms of using the definition, it could be anything, right? So for instance, I can book you something like I don't remember exactly, but it could be something like you could have the P sub 2 of R and then cross with maybe let's say R3 here, right? So that's possible. So in that case, that means your first vector space is this all this polynomial vector space, right? All the polynomials degree less than or equal to 2, and then your second vector space is going to be of our standard like Rn there in terms of n equal to 3, and then so what will be like an element belonging to this product space, right? Well, then you can take something like maybe 3 plus 5x minus 7x squared. And then the second one, or sometimes we write as a row, sometimes we write as a column, not matter, right? Maybe there's something like, 1, 2, negative 4, right? So this will be an element belonging to this new, well, at least right now, this is a new set, right? Eventually, we're trying to prove, equipped with the product and a scalar multiplication and the sum, then this product space is still a vector space, right? But everyone can see here, this is well, in this case, it's really quite unique. You kind of paired a polynomial space with the Rn here, all right? But more familiar to us is probably something like if you have the R times R, right, then that will be like A and B here, where both A and B are belonging to arbitrary real numbers, right? So that is we do the cross product between two, right? Of course, you can have R cross maybe another R, right? So then that's give you not an ordered pair, but an ordered triple there, right? So those are some basic examples of the products of vector spaces. And then 3.73, I believe this one basically claims, suppose that, so V1 are up to Vm are vector spaces are over the same field F, then the conclusion is the V1 times V2 times up to V sub m. This is also a vector space over F. All right. So this proof, I think, by assuming V1, V2 each individual one is a vector space, right? And then by the definition just right above, then it's very easier to check all the properties for a vector space are still holds for this new one. So we'll leave the proof as an exercise to everyone. But after we introduce this theorem, I think we're confident to say now if we have this new product space, we know it's a vector space. And then the next thing we care about is the dimensions. I think that's 376, it's the dimensions of the vector of this new space. So this also, I think, a very intuitive, seems a natural result. So we are assuming these individual ones are finite dimensional vector spaces. finite dimensional vector spaces. All right, then this V1 cross times V2 at up to V sub m, this is also finite dimensional. And we can have an exact way to calculate the dimension of this new vector space, which is given by this equation here, saying the dimension is, well, the dimension of the V1 plus the dimension of V2, right, and then plus the dimension up to the V sub m, right? So that's a very natural result to think about this. And the proof basically is constructing a basis and then counting how many vectors in that basis. And then the way to construct a basis is, well, if V1 has some basis, then you take the first one and then make all the other components in that cross product space equal to 0. And then you take the second one and then make all other positions equal to 0 and so on, right? So if you keep doing this, let's say if V1 has 5, then that's going to give you like 5 vectors in this new product space. If V2 has 3, then you're going to make 3 vectors are in this vector space V1 up times Vm and so on. So then once you add all this together, combine all this together, that's going to be useful to represent everything in this new vector space. And then that's, you also probably have to kind of discuss this, those vectors are linearly independent. So then they form a basis. And if you count how many there by the way of the construction, well, each vector in the basis of V1 contribute to 1 vector in this new set. And then each vector in the vector space V2 contribute to 1 vector in this new basis set, and so on. So of course, then if you counting the numbers, it's the dimension of the V1 tell you how many vectors in the basis of V1, and then plus the dimension of V2 tell you how many vectors in the dimension of V2, and so on. All right. So that's a natural way to complete this proof. So we're going to write a few sentences to kind of make it more clear, specific about what we said. All right, but I think the idea here is very natural. There's no much like tricks here, or it's not very hard to prove. So we're just going to choose a basis of each v sub j. Of course, here the j is from 1 to m. All right, so for each vector space, you choose a basis. Remember that the basis may have multiple vectors there. All right, so then for each basis vector of each v sub j, for each basis vector, so this is a vector from that basis. All right, so it's a single vector here, of each v sub j. All right, so we consider the element. All right, so we're going to use this to create a vector, or what you call element of this new product space that equals the basis vector in the jth slot, and 0 in the other slots. Okay. So then this list of all such vectors is linearly independent. So we're just claiming that. I mean, strictly speaking, we need to verify this, but it should be pretty straightforward to check this. It's linearly independent, and we also claim this list spans the product space. Then it is a basis of this new product space. And then the way we construct this tells us the length of this basis is dimension V1 plus the dimension V2 up to the dimension V sub m. Then we complete the proof. So using that example we mentioned above, we said if you have a polynomial like a P2 sub P2R across maybe like R3 here, so then what is the basis for this? All right, so that can give us a specific way to say this. Well, the idea is you're going to take the basis of P2 of R, right? So which going to be, we'll use the standard one, let's say 1, and we have x squared right here, and then the basis of R3, we have like 1, 0, 0, 0, 1, 0, 0, 0, 1. We have this, and then so basis of the product will be, if we follow the proof, right? What we're going to do is, remember when you have this is the product of two vector spaces, right? So really every vector in this new product space is just the ordered pair. It's just an element with two entries separated by the comma. We care about the order, right? The polynomial go first, the R3 go second. So then this one, if you list the basis here, well, we can take the 1 here, right? And then you can take any of this. So we probably match this with 1, 0, 0. Right, that's the first one. And then we have 1, and then we can match with, maybe I should make this a little smaller. All right, 1, 0, 0. And then we have 1, and we have 0, 1, 0. Then we have, and the same 1, this is a constant polynomial, 0, 0, 1. And then we have x, and then match with each of this basis vector in R3. 0, 1, 0, and then x here, 0, 0, 1, right? And then we're going to have x squared. So we're trying to have, my fault, okay. So this is not we overdone this, all right. So we are saying is we want to have, okay, so we want to have 1 here, and then we have a 0. All right, sorry about that. So we have 1, 0 here, and then we have, well, we already used 1, right? So then, because we want x, and well, make it clear, this is a 0 in R3. So we have this one here, and then we have x, and 0, 0, 0 here, and then we have x squared, and 0, 0, 0, right? That's what we should do. Sorry about that. And then after that, so this is like you take each basis vector from the V1, and then put in the first component in this cross product space, and then all other slots, well, we have just one other slots in the second slots there, you put it as a 0, and then you're going to take the basis from the V sub 2 in this is R3 here, and then this is a 0 polynomial, 1, 0, and then this is 0 and 0, 0, 1, right? Yeah, that's the right way to construct it. So we have the dimension of this is equal to the dimension of P sub 2 of R plus the dimension of R3, which is 3 plus 3, which is equal to 6. All right, so that's the right way to form the basis. All right, and this is a specific example. So once we have this one, then the next thing is we're going to build along multi-steps, or maybe some kind of propositions or theorems and definitions, but eventually, as I said in the beginning of the video, we're trying to show the dimension of the direct sum is the sums of the dimensions of those vector spaces. So in order to achieve that, let's first make a definition here. We define, I think this is 377, this one, we're going to make a definition saying, suppose that we have the U1 up to UM are subspaces of V. So we're going to define a linear map. Actually, the definition claim it's linear, but it's always a good idea to verify that. But we're going to define linear map gamma, which is from the product space U1 times U2 up to UM, and then connect this with the sum U1 plus U2 up to UM. And then this definition is pretty natural, saying, well, because anything in this cross product space will be like a U1 up to UM, right? This is generic notation here. And so how you're going to map that element to the sum? Well, we just add all those components together. And it's making sense to add all those components together because we are looking at all those U are the subspaces of the same vector space V, right? So then at least when you add this together, that is still becoming element in the V, and the V is a vector space, so it's closed under addition, right? So we can, we can now say, well, you make the polynomial and maybe then R2 and maybe a C5, and then add all this together. That's not making sense, all right? So here, all those U's are subspaces of a vector space V here. So this definition is well-defined, and it's a very natural way, and everyone should check this is linear, all right? But then, so this is our definition here, and then actually we are trying to claim here is then, so this will be actually more like a theorem or proposition here. I don't know what we call that, right? But then the conclusion is the sum here is a direct sum if and only if this linear map gamma is injective. Or is injective. Remember, injective means like that a linear map is one-to-one, right? Different inputs go to the different outputs. Or the same way to say that is if you have the same y value or same output, then the inputs must be the same. All right? And for an injective map, we have a lot of properties we proved in an earlier section when we study a linear map is injective or surjective, right? And this one, actually, a couple of things immediately notice here. One is by this definition of the gamma function here, or the gamma map here, this one is obviously is going to be also a surjective. All right? So this one is the domain there will be this product space, right? U1 times U2 up to UM. And then the codomain, right, on the other side, the set is the direct sum, U1 plus U2 plus UM. However, if anything you taken from that sum, right, you take a element U1 plus element U2, then you can always find the preimage, right? You just make that vector U1 comma U2 up to U comma UM, right? So this tells us anything on the receiving end, you can find a preimage from the sending end, right? So that tells us this is actually also a surjective, this thing. All right? It's always a surjective. But now what we're saying is if this is injective, and then this will be a direct sum. If that's a direct sum, then this is injective. So we have to recall two properties for our proof. All right, we're going to write down that, refer to that along our proof. But one thing is, in order to check a sum is a direct sum, one proposition saying is if 0 can only be written as 0 plus 0 plus 0, right? Then if 0 in that sum, the only unique representation is the sum of all the 0 elements from those U1 up to UM, then this tells you that the sum is the direct sum. That is the if and only if statement. And the other thing we're going to use is, well, in order to take advantage of this assumption like gamma is injective, or prove gamma is injective, we have an equivalent proposition saying the gamma is injective if only if the gamma of input equal to 0 implies that the input is a 0 element in the domain. All right. So that is something, a proposition, I think is a proposition, I think it's 316 or on page 61. We're going to refer to that. But these two things we're going to use. All right. And this theorem of propagation itself is a biconditional statement. So strictly speaking, we're going to prove both ways. All right, so we're going to do that. The book kind of condenses that in a very nice fashion. I'm going to explain that a little bit here. All right, so we can assume one direction prove the other. Does not matter which one you do that. For instance, you can assume if we prove this direction, we're going to assume like u1 plus um is a direct sum. All right, then we want to prove the gamma function defined in 377, this is injective. So that prove one direction. All right. So by our assumption, all right, well, let's consider this, right? So if that's a direct sum, so let's consider if you have gamma of u1 plus equal to 0, all right, then by the definition of this function, the gamma u1 plus, gamma, this is not the sum here, this is the vector here, right? So then gamma of this equal to 0 means what, right? Well, the gamma function is, if you look at here, we actually have in the middle of the screen here, this is the u1 plus all right, that's the output. Your input is this in the pair of parentheses, it's u1, u2 up to right? Your output is the sum of those m vectors, and then from different subspaces. So then gamma equal to 0 means this sum is equal to 0. And then by our, that is the proposition 144 on page 23. All right, so that proposition basically, as I mentioned here, tells us the 0 has a unique representation. It's just the sum of those 0 elements from each vector space, u1, u2, and so on. All right, so this, then by this proposition, we already, our assumption is this a direct sum. So then, since this representation is unique and all the individual uj should be 0, so that tells us this is equal to 0. All right, so that tells us this u1 up to is a 0 element. Right? So based on the assumption we have a direct sum, we showed if gamma of u equal to 0, then that u is equal to 0. So then this tells us by the proposition 316, right, on page 61, this tells us the gamma is injective. Or injective means if gamma u equal to 0, then u is equal to 0. Or that's actually is a if and only if statement. We use one direction. And then the other proof we're going to do here is to basically reverse what we did, or because the two things we referred to are both equivalent conditions, so we can easily reverse that. All right. So let's say conversely, let's assume this gamma is injective. All right. So then we want to prove this u1, is a direct sum. Okay. So when you're trying to show something is a direct sum, so we are going to consider the u1 plus u2, right? Maybe better to say just let this is equal to 0. All right. So if you can show the only way to make this equation hold is to have u1, u2 up to equal to 0, then by that proposition 144, then this is a direct sum, right? So we let this equal to 0, then the gamma of this u1 up to right, is equal to 0, right, by the definition of gamma, because this gamma of this vector is the output is u1 plus u2 up to right? So this is equal to 0. And then since the gamma is injective, so this is our assumption, then this tells us this must be equal to 0. Right? This is by that proposition 316, again, or on page on page 61. So this equal to 0. All right. So then U1, U2, each individual one, all equal to 0. Right? So by 144, all right, so then the sum is a direct sum. Okay, so this proved something. I think if you look at this now, at first I think it's not that hard of a proof, or it's make a nice connection with something we learned before. The other thing is the reason we define such a natural like map gamma is going because we want to use this to prove the theorem, and which is I think the number is the 378 here. So we're going to use this to prove the 378. This one says a sum. Well, let's make assumption first. So let's suppose V is finite dimensional. Right, and U1, UM are subspaces of V. Right, then this sum is a direct sum if and only if the dimension of U1 up to UM is equal to the dimension U1, right, plus dimension U2 plus the last one is the dimension UM. All right, so that's what we're trying to do here, using that gamma map to help us to finish this proof. All right, and this proof I think is also very natural, intuitive fashion, right? Because if we have a sum which is a direct sum, then if you take any two subspaces Ui and Uj, right? Suppose I not equal to j, then the only common element is the 0 there. So basically, they kind of like we would not say disjoint because there indeed the 0 is in every vector space, right? But it's almost like a disjoint. So then there are no other overlapped elements. All right, think about why is that? All right, and then that way it's pretty natural to say, well, then when you add this together, then in order to make a basis for the sum space, if they're direct sum, in order to make a basis, then you're going to just take the basis from each individual ones, kind of like what we did before. And then, so you will add the dimension of the first one, the second one together, or count how many there, hopefully give you all this. All right, so it's kind of, I think it's not hard to believe this, but in order to make the proof, we wait until the very end of the chapter 3 to do this. All right, so here is one way to prove that. All right, so let's first make a remark or observation here, saying, observe that gamma function in the 377, this is surjective. We already said that we're going to formally write this down. It's surjective. All right, and then so then that implies, which gives us the range of the gamma is equal to the U1 plus up to UM, right? Because if that's a surjective, that means the range is just everything on the other end. All right, and then the reason we're doing this is because we're going to try to take advantage of something we built in this section, but also remember we have the fundamental theorem of linear map. That's the dimension of the V. If V is a finite dimensional space, the dimension of V is the dimension of the null space of T, and then plus the dimension of the range, right? So that's what we want to use. So now let's use that by the fundamental theorem of linear map. All right. So we have what, right? So originally, because remember your gamma is the map we're talking about here, right? And the gamma takes the U1 cross U2 cross U sub m to U1 plus U2 plus up to U sub m. All right, so your dimension here will be the domain here will be the U1 cross U2, and then times UM, and then the original version saying is this is equal to the dimension of the null space of gamma plus the dimension of the range of the gamma, right? This not the null space and the range, generally speaking, are not even in the same vector spaces, right? Because if your gamma is from some U to some W, then one is in the U space, another is in the W space. So, but we know the range is equal to, by our discussion above, right? We know the range is equal to the sum. So since the range of gamma is equal to the sum of this vector spaces, then the dimension of this multiplication here is equal to the dimension of the null gamma, and then plus the dimension, well, since the range is the same as this one, so it's equal to the sum, all right? And what next? Well, what is the dimension of those product space? Well, that's something we talked about probably like 10, 20 minutes ago, saying, well, the dimension here, this is equal to the dimension of U1 plus the dimension of U2 plus the dimension of UM. That's the population we did earlier in this recording. Then from here, so we have the dimension U1, and then plus the dimension UM is equal to the dimension of null gamma, and then plus the dimension of this one. So we're almost getting there, all right? So using the population we have built, we get so far, right? This is just based on the population we have done, and keep in mind, we have not even considered the gamma is injective or not, right? And that's something we haven't used yet, or in other words, we have not considered this sum is a direct sum or not. So in order to make this left-hand side is equal to just the dimension of the U1 plus U2 plus UM, we observe that this, right now we have the extra term there, right? So if you want this equal to this is if and only if the dimension of the null t is equal to 0. The gamma is equal to 0, right? But if this equal to 0, then of course the left-hand side of this one here is equal to the right-hand side, just a single dimension of the U1 plus U2 up to UM, and then vice versa, right? So this is if and only if statement, and then the dimension of null t equal to 0, this if and only if the null t is equal to 0, right? Only 0. But that means if and only if this, gamma, I'm guessing t here is gamma, the gamma is injective. Okay, and then, but by our discussion earlier, why we built that gamma function, we're saying is, let's go back to here. This is what we're saying here is gamma is injective if and only if the sum is a direct sum. That's a 377. So by 3, so this is if and only if this sum is a direct sum. This is by 377. So now we can see, in order to achieve the result, or the dimension of the sums of the dimensions equal to the dimension of the sum, then this becomes if and only if the sum is a direct sum. All right, that way we completed the proof. All right, so this is the main thing we want to accomplish in the first recording of the section 3E here. So in the next recording, we probably need 2 more, or probably next 2 recordings, we're going to actually move to a new concept. It's called a quotient space. And then we're going to actually also define the sum and the scalar multiplication there, make sure it also become a vector space, and then talk about dimension of that related to the V and the U there. So that's what we're going to accomplish in the next 2 recordings. All right, so thanks for watching, and I will see you in the next recording.